What's up, everyone? This video is to introduce our topic of fluids, and we are going to start with something actually rather simple. It's going to be fluid statics. Fluid statics, as you can see written here already for you, is the study of stationary liquids and gases. It's important that you know that a fluid is anything that takes the shape of the vessel that it's in, and that is a liquid or a gas. The first place we're going to start with this is, as you can see here, is stationary stuff. No flowing waters yet, but stationary fluids apply pressures on objects. Now, pressure is defined as force per unit area. Pressure, letter P, is defined as force per unit area, which is Newton per meter squared, measured in pascals, PA, and sometimes in atmospheres for like atmospheric pressure. You may know about that as well. Maybe you did that in chemistry. So what's causing this pressure is the weight of the fluid above you pushing down on you, and then the air molecules are actually hitting you, creating pressure on the surface of your body and all around you. So let's take a look at that pressure with this amazing app brought to you by PhET Simulations at Colorado University. Now, I'm going to turn the atmosphere off for a minute, and I have a fluid in there, and let's check out some of the pressure here. So, interesting. At 0, well, we've got 0. Let's go to 1 meter. At 1 meter, this fluid is exerting roughly 10 kilopascals of pressure. That's the weight of the water above pushing down on this object and creating pressure. Again, the molecules are applying a force over the area of this object because the molecules are actually hitting the object. Maybe you learned about in chemistry, like kinetic molecular theory or something like that. But then let's go to 2 meters. We've doubled the depth and we've doubled the pressure. I'll stop talking like that. I'm sorry. And then if I triple the depth, guess what? Well, the app breaks, but you can imagine it's triple the pressure. So depth is directly related to the pressure. Let's check out how fluid density would affect it. So let's put this puppy back here at 10 kilopascals. And let's change this to, I don't know, what do they give us? Gasoline. Nothing like going for a swim in gasoline, I guess. Why are we doing that? It's 7 kilopascals at that depth. And then if we double the density, I believe, to 1400, which is apparently honey, you get double the pressure. So it looks like pressure is directly related to density. So let's take a look at that gravity. Gravity, let's see. We go to low gravity, 1. We have a pressure of 1. If we go to, let's say, 10 meters, oh, we get about 10. What a coincidence. So it looks like all these things are directly related to pressure. The height above you in terms of how much fluid is above you, the amount of gravity, and the density. So let's put that all together. Are you ready to derive? I am. So exciting. New math. Assuming I could change the color here. Here we go. We've got, I don't know if you know this from chemistry, but density is mass over volume, which is kilogram per meter cubed. Okay, and this is Greek letter rho. It is not a P, like the letter P. It's a rho. It looks like rho. Isn't that amazing? Fun to draw. It's measurement of density. Let's put this all together, and we get power. Good job, Josh. Pressure is force over area. And remember, that force is the weight of all the fluid above you. Literally, the weight, as in mg over the area. Now, if I rearrange density, or for mass, I get mass equals density times volume. So I can make this density times volume times g over A. A being the area, but volume is meters cubed, area is meters squared. Cubed over squared just becomes meters, as in height. So this just becomes rho GH. And that's the expression that you would probably expect because we just saw that the pressure is directly related to the density, the gravity, and the height. So we just derived an expression. Wasn't that great? Felt good over here. So we have that gauge pressure. This is just gauge pressure. The amount a pressure gauge would read is just rho g h. Now, back to that simulation. Don't forget, like this was going swimming apparently in gasoline, but we're going to go with just water for now. And I turn the atmosphere off. If we turn the atmosphere on, notice the pressure increases a lot, okay? There is an atmospheric pressure because we live in a sea of air above us that applies a pressure down on us. So we have to include that as well. Right now, your body is exerting 14.7 pounds per square inch out to counter the pressure of all the weight of the air above you. So we have to include that as well. So let's show how that shows up in the math. Okay, we've got, scrolling. Here's the equation. This is what's on the AP equation sheet. It is pressure equals P naught plus rho g h. So let's define these things real quick. P is absolute or total pressure. PO is the atmospheric pressure. It's a big word for me to spell. Atmospheric pressure. For us, that pressure is 101,300 pascals, or 1 atmosphere. And then rho GH, as we've already defined, is the gauge pressure. So this is the pressure of just the fluid by itself without the atmosphere. So if we're including the atmosphere, we literally add P naught. If we're not, we don't. It's pretty simple. Let's see how this goes. So I have an example. Oh, before we do that, I want to show you something else. It's fascinating. Check out this amazing simulation. So here's another tank of water. Okay, and notice how there's like different shapes. You know, one side is a triangle, the other one's like an upside down triangle. Check out this pressure gauge. Let's turn off atmosphere because who needs to breathe? And so we have 10, 20, here's 25, and there's a wide area of water. What's interesting is if I go over here to 20, same spot, it's 25. Here, 20, 15, 10. You get it, 10, 15. It's the same thing. The important thing to notice here is that regardless of the shape of the vessel, the pressure is the same at all depths. So why don't we make a note of that? Crazy how that just showed up out of nowhere, right? That's an important concept. So let's move on from there and let's do an example together. Are you ready? I'm excited. Your first pressure question. This scenario is somebody swimming pretty deep, 10 meters, that's like 33 feet deep in ocean water, seawater. And I don't know about my drawing, but I'm kind of curious if they're swimming or something bad happened and now they're 10 meters underwater. But let's figure out what the pressure this person experiences at this depth. So here we go. We have our expression that says, what does it say? I believe it says pressure is P naught plus rho GH. So atmospheric pressure plus gauge pressure. P equals P naught plus rho GH. So the pressure in this case is going to be our atmospheric pressure above us, 101,300 pascals, plus the gauge pressure, which is the density of seawater, kilograms per meter cubed, times 9.8 meters per second squared, times the depth, which is 10 meters. When you put this all together, the pressure that you are experiencing is 202,240 pascals. That's a lot of pressure. Is it? I don't know. So that's it. That's how you found the pressure at that depth, including the atmosphere. Okay, but here's an interesting question. At least I think it's interesting. But what do I know? How much force is being exerted on your body? I was wondering about that. Like, so the pressure is one thing, but what is like the total force that this would apply to you? So randomly, I Googled the average surface area of a human being, and I got, so first of all, pressure is force over area. I want to know what the force is on your body. So I need your surface area. So I get force equals pressure times area, and it's 202,240 pascals, times your area, which is 1.9 meters squared. And it's a lot of force. It's roughly 384,256 newtons of force. That seems excessive. So there's that. Okay? Basic pressure example. Shall we move on? I'm excited to move on. There's something called a YouTube manometer. Manometer, not manometer, although manometer is kind of fun to say. It's a YouTube manometer. It's basically, you may have seen one in chemistry, it's a U-shaped tube, basically. If it's closed, it's not exposed to the atmosphere at all, and if it's open, it is exposed to the atmosphere. Right now, I've got some oil in this YouTube manometer. The side on the left that's blackened out here, that side is closed, okay? And what we're trying to figure out is what is the pressure right there? Like how much pressure is being exerted on that cap that holds everything together? So what is the pressure there? Good question. Thank you for asking. Well, one of the cool things we know is that a fluid has the same pressure everywhere based on height, regardless of the shape of the vessel. So it would be really, you can see like I have that dotted line there, but if I could figure out the pressure right here on that side of the tube, it would be the same as the pressure here on this side of the tube. So how do I figure out the pressure there? Well, it's just the pressure equation that we have. It's nothing too crazy. So let's go with, first, let's try the closed scenario. Closed means no atmosphere. So that the pressure is just going to be no atmospheric pressure. So just P equals rho GH. In this case, that will be the density of the oil, which was 700 kilograms per cubic meter, I believe. Oh, it's right above it. Look at that. It's right there. Isn't it great that I barely edit these videos? All right, so we got 700 kilograms per meter cubed. We've got 9.8 meters per second squared. We've got 0.1 meters. So this pressure is 686 pascals. Okay. Not a lot of pressure created by the fluid itself. But if it was a closed system, open, so we're open to the atmosphere now. I'm going to go with green. If it's open, remember, open means the pressure, the total pressure is the atmospheric plus the gauge. So in this case, it would be 101,300 pascals. Why did I put parentheses around that? Nobody knows. Plus the gauge pressure, 686 pascals, gives us a total pressure of 101,986 pascals. Yay. Now we know what the pressure would be if it was an open tube. How nice. All right. Let's close this puppy out. Oh, by the way, this diagram here goes with number 4 on our homework in the year of 2025, just so you could see the pictures provided, but I just wanted to make it clear that this is what goes with the diagram and the measurements. All right. So first things first. Pressure is force over area. We got this pressure by saying it's the weight of the fluid above us, and through that we derived our expression for the gauge pressure just based on the fluid acting on us, which was density times gravitational acceleration times height. And from there, we talked about the expression for total pressure or absolute pressure. It's the combination of the gauge pressure we're feeling from any liquid or gas plus the atmospheric pressure above us. These numbers you do not need to memorize. The 101,300 pascals will always be provided. Now, all depths have the same pressure regardless of the shape of the container. That's another important concept. But other than that, there's really not much to this. You're simply subbing in numbers to our expression and just getting used to the new math. It's not too difficult. But the key concept here is that the depths have the same pressure. So if we go back up to this picture here for number 4, you notice I've drawn a dotted line right here. And that means whatever the pressure is for that blue fluid at that depth must also be the pressure for the orange fluid at that depth. Interesting. So right here, the orange and blue must be experiencing the same pressure. That's about it, peoples. Not one of my best videos, kind of thrown together during 5th period when I had a little free time, but, I'd still give it 3 out of 5 stars. Hope it was helpful.